Hi, my name is Amani Smith, and this is my lab report for lab number 6. So, for the introduction, the purpose of this lab was to observe and make predictions about induced currents from magnetic fields that are being changed using Faraday's law. And here's a quick preview of the results. For the experiment, I got 1.35 seconds for the magnet to drop, and then for the computational results, I got 1.308 seconds. So for the key principles, the main one that we're going to be using is Faraday's law, which states the relationship between EMF and the phi dt, which is the change in flux through a surface. So a change in flux is going to induce a current. And then we also have the Biot-Savart law, which gives the relationship between the magnetic field and current. So for our experiment setup, we're going to drop a bar magnet down an aluminum tube and measure the time of the drop. And the reason why we're using aluminum compared to steel is because aluminum is more conductive. And this is going to basically simulate Faraday's law, where we're going to have a changing magnetic field creating an induced current within the aluminum, and this magnetic field caused by the induced current is going to oppose the motion of the falling magnet, therefore slowing down its motion as it's falling down the tube. And we're going to make a couple of assumptions. Number one is that the system only pertains to the magnet and the aluminum tube, and we're going to assume that the bar magnet is a magnetic dipole. So here is our data. We got the dimensions of the tube. The aluminum tube that we made had a length of 0.46 meters and a radius of 0.02 1 meter. And then for the trial, for the first one we got 1.38, 1.28 for the second one, 1.29, and then 1.38 and 1.41, and then we average this to get an average time of 1.35 seconds. So here for the computational model, we use GlowScript. Right here is the code for the B field, and right here I wrote the code for the flux going through the aluminum as the magnet is falling. Here for the last two steps, this handles the forces on the magnet as it's falling. As we see right here, the net force on the magnet is going to be 0 as it's going through the tube. And then we have more code down here handling the changing velocity and position of the magnet through its motion. So while our experimental data is fairly close to our computational results, there are some differences, and this could be due to potential sources of error, such as the neglection of external forces, the neglection of air resistance, and we also could have made measurement errors with our timer. Now for the discussion questions, which side of the computational visual model is counterclockwise or clockwise for the current? Using Faraday's law, we can see that the red side is going to be counterclockwise and the blue side is going to be clockwise. Now what happens if we flip the magnet? The motion will stay the same. It's still going to be slowed down as it goes through the tube. However, the current will run in different directions. So the red is going to be clockwise and the blue would be counterclockwise. Now, how does this compare to our experimental data? As said before, they're fairly similar, but our data could have been better if we gained better measurements throughout the experiment and conducted better measurements, especially with timing. And now, how does the shape of the graph, what does that tell us about the motion of the actual bar magnet? Well, it tells us the relationship between the gravitational force and the magnetic forces. As we can see here, as the magnet is falling through the two are balanced, so there's no acceleration, and it just has constant velocity. So now what would happen if the resistivity of the conductor were reduced to close to 0? Well, the current would increase using Ohm's law, and this would cause a slower fall due to the increasing current, which would increase the induced magnetic field by the aluminum. So now what if holes or slots were cut in the tube, and how would this affect the ring current within the model? Well, this would decrease the current, and a decrease in current would decrease the induced magnetic field, causing a faster fall as the magnet travels through the tube.